So I'm going to continue on from where we got to this morning. So if you remember, we were discussing asymmetric exclusion process. And we had derived equations for the evolution of the density. So so this is the TASEP continued, so it's section 3C continued. What we derived was I by dt equals P I 1 minus I minus Q 1 minus I minus I minus P that's what we derived. And in fact, this was a continuity equation. So this was the current going from the net current going from I minus 1 to I, minus the net current going from I to I plus 1. Okay, so that's where we got to. So one thing to note, in the case P equals Q, then you get a big cancellation. So, for example, this term here, tau I minus 1 tau I, the minus, cancels with this one here. And so you get a big simplification. And so in the case P equals Q only, we get this form. So okay, you can check. And if you compare this to the random walk equation, remember when we had the probability of a random walker, symmetric random walker, it's exactly the same equation. Excuse me, I minus 1. So you can solve this equation, and the dynamic exponent will be 2, as I claimed in the first half of the lecture. But remember, this is a very special case. P equals Q, and that's because it's a detailed balance case, and you have no current flowing. So you see it's much simpler in that case. Sorry? Oh, yes. Very observant. Okay, so this is the same as the random walker, which was in lecture 1, equation 7. So I managed to label that equation. And so Z, the dynamic exponent, is 2. But the general case is more difficult. So, okay, from now on, we'll consider TASEP. So this is the totally asymmetric simple exclusion process. So this is the case P equals 1. Q equals 0. And also, I'm going to be interested in open boundaries. So we're going to have to augment this equation. Remember, this was away from the boundaries. If we're at the boundaries, we're going to just have to augment this equation. So our open boundaries at the first site then the current, we can just write it down. I'm not going to derive it microscopically, just write it down. The current, remember, so we're looking for the current coming in, the net current coming in. Well, we know we put particles in at site 1 with rate alpha if site 1 is empty. So that gives me this correlation function, 1 minus tau 1. It's the average, the probability that the first site is empty. And then I just get the second term will be tau 1, 1 minus tau 2. Remember, I'm in the P equals 1 case, so P is just set to 1. And also, if I wanted to do it right here, at site L, the final site, well, I lose a particle with a rate beta. So I have minus beta tau L. And then I gain particles from L minus 1 due to a current term. Okay, so now I'm just writing down these equations. We should be comfortable with them. They're kind of obvious once you get the hang of it. So these are the additional equations I need at the boundary for the open case. So one thing I want to stress is actually this equation here. Even for p equals 1, q equals 0, it simplifies a bit. But you have a hierarchy, what we call a hierarchy of correlation functions. Here, this has just got one torr, so it's a one-point correlation function. But here, we've got two-point correlation functions. So if I also, once you get a bit of experience, you can just write down the equations. So you might say, well, all I need here is this particular correlation function, the J1, which corresponds to, well, the one that represents a current, which corresponds to a torr I and then a 1 minus torr I plus 1. So why don't I try and write down the equation for that? So if I do so, and I'm doing this quickly because I have some experience, but you can check. If I want to write down the equation for this correlation function, then I just need to think about loss and gain terms. So here I've got, it's the probability of there being a particle here and a vacancy there. So I could have got that. The probability coming into that is if this particle came from this site here. So in fact, I would need torr I minus 1 and 1 minus torr I, so torr I empty. But then I need also, and then I would lose probability from this guy hopping forward. So I get a term minus torr I, 1 minus torr I plus 1. And then I could have got this vacancy from there being a particle there and it hopping forward. So I get another term, excuse me, torr I plus 1. Okay, so I can do that quite quickly. With a bit of practice, it becomes obvious how it works. But the point I want to make is that, again, this is a two-point correlation function. And on here, I've got three-point correlation functions. And however hard I try, I won't get a closed set of equations. Well, I will do if I go up to L-point correlation functions. But that's a big set of equations. Sorry? Second term comes because this particles can hop from here to here. I'm sorry? No, that one, no. These ones, yes. Okay, but anyway, generally it involves three-point correlation functions. Okay, so usually that's a hard hierarchy to crack. It's often called the bedrock problem for many body systems, is that it's difficult to get closed equations. Turns out, as we'll do in the second half of the lecture, we can get some exact solutions in this case. But for the moment, the first thing usually you do when you have a hard problem in statistical physics is you try and make a mean field theory. So all mean field theory is, it's a simple approximation that ignores correlation. So that's what you will have learned at undergraduate. The name mean field sounds a bit strange. It just means you try and ignore a correlation in the easiest way or the most appropriate way. And in this case, the mean field theory is very simple. You just ignore all correlations. So let's now, this is section 3D, let us develop mean field theory. So as I said, it's an approximation. So the simplest approximation that will close this hierarchy is any correlation function, let's say tor I, tor j, we just say is equal to the average of tor I, average of tor j. So we ignore correlations, because in general this is not true, there's some correlation. But we just say no, we approximate it as zero correlation. And let me just change notation, and I can call this is the average of tor I, so it's just a density. Let me just, to lighten notation, just put rho I, rho j. And similarly, 3-point correlation functions I just write as a product of 3 densities. So it's a really, you would think, very crude approximation. It's the simplest mean field theory. It's the crudest mean field theory you can do. You ignore all correlation. But remarkably, it works pretty well, as we'll see. So if I do this, then this equation here, let me call this equation 1. And remember, I'm in the case p equals 1, just to make life a bit simpler. So I just have these 2 terms here. What it becomes is the rho I by dt equals rho I minus 1, 1 minus rho I, minus rho I 1, minus rho I plus 1. And so now it's just an equation in terms of the variables rho. So there's still a bit of work to do, but there's some hope now that we can solve this. And okay, to make life just a little bit simpler, I could work on the lattice. I'm choosing to use the continuum approximation that we've sort of introduced in previous lectures because it makes life a little bit easier, I find. So continuum approximation, we don't have to do this, but I think it makes it a little bit easier. And we still get the same phase diagram, which is what we want. So now make continuum approximation. So remember, we introduce a lattice spacing, so we say rho I plus or minus 1 becomes rho. Continuum approximation, is x is equal to I, the lattice position times A, the lattice spacing. And okay, so I plus or minus 1 becomes x plus or minus A, which we end up writing, expanding to second order, is rho x plus or minus rho dashed of x plus a half rho double dashed of x. Excuse me, I should have an A there. Now here I'm using this expansion as an approximation, so I'm not trying to be rigorous and prove any hydrodynamic limit. I'm saying this is just a continuum approximation. It will do the job for me. So I just set A equals 1. And hopefully you'll be convinced that actually this is fine. All we need to really keep is the second order terms to capture the effects of stochasticity. We don't need to go any further. It will just make life more difficult. Okay, so I set A equals to 1. And then, okay, then I substitute this in this equation. And what I get, once I do that, is what I find is d rho by dt equals, okay, so right, let me keep the a's in there just for a moment. A rho dashed 1 minus 2 rho plus a squared over 2 rho double dash. And I now set A equals 1. And I can write this now as d rho by dt equals, and let me write it in this form. So I go back to writing it as a continuity equation. So d by dx of j. And now j takes a nice form. It's rho 1 minus rho minus a half. Okay, then d rho by dx. So remember, j is the current. So if I look at this, I see 2 different bits. So this bit is coming from the asymmetry of the particle motion. And this is called the advective current. Whereas this bit here, if you remember from your basic physics, if you have a diffusion, will give you a current when there's a concentration gradient. And that's exactly what this is saying. You get current down a concentration gradient. So this is the diffusive current. This is important, that the current in this mean field theory is made up from two parts, advective and diffusive current. Okay, so we want now to study this equation. So in this lecture, okay, let's forget the time dependence. We'll leave that story for another time. I want now to look at the stationary state. So the stationary state, d rho by dt equals 0. So I'm going to have 0 equals minus dj by dx. That tells me straight away that j is a constant, as you expect. So all it's saying is that, well, if we have a stationary state, so the density is a constant, then the current going into a site must be the same as the current going out, or else the density wouldn't be constant. It would be growing or decreasing. So that it's trivial that the current, when we have a conserved quantity, must be the same everywhere. So we get that for free. So then J is a constant, and I can rewrite this equation as, okay, so yeah, this, let me label this as equation 3, this stuff here. So the steady state, it becomes a half d rho by dx. Yeah, okay, so now it's a steady state, so there's no time dependence, so I can just write rho dash, so d rho by dx equals, then it will equal rho 1 minus rho minus j, where j is now constant. But also I've got boundary conditions, and remember the boundary reservoirs I can treat as rho 0 equals alpha, and rho of L equals 1 minus beta. Okay, that's what the boundary conditions correspond to. Okay, so now it's just a mathematical problem. I want to solve this first order differential equation subject to these boundary conditions. The only non-trivial thing is that J is a constant, and the constant will be determined by the boundary conditions. So that makes it a little bit tricky. The constant is fixed by boundary conditions. So what we want to do is to actually somehow look for consistent solutions. And the easiest way to do that is, in fact, graphically, rather than trying to solve this equation, which you can do, you know, with some functions. It's easier just to look at what happens, like draw a picture, and then it becomes clear what's happening. Okay, so this is the derivative, and it's equal to this quadratic, right? So if I sketch that, so I'm looking at the derivative of rho dash, well, over 2, against rho. And it's some parabola like this, right? Because I've got a minus rho squared term, easy. So it means that the derivative is 0 at two particular values, rho minus and rho plus. And these values are the roots of this quadratic. So rho plus minus is going to be, if I work out that quadratic, it's 1 plus or minus the square root of 1 minus 4j all over 2. Okay, simple, just that's the roots of this quadratic here. And of course, I just note that rho plus rho minus is equal to 1. I note that for later. Okay, and I'm forgetting to label my equations again. This is the set of, as I said, this is the equation for rho that I want to solve. So actually, from this information, The final thing is that, well, actually, I said that these are zeros. But to have zeros, I need that the parabola is high enough. And in fact, the maximum value of the parabola is when rho equals a half. So I see the maximum value of this function, if rho equals a half, this is a quarter minus j. So to have this bigger than 0, I need j less than a quarter, right, to have these two fixed points. So now I can sketch the solutions. So if j is less than a quarter, then I have these, okay, so at these densities, the rho by dx is 0, so rho becomes a constant. So I can have a solutions. So rho plus and rho minus. So if I start up here above rho plus, then I see that rho dash, okay, I'm down here, is negative. And so what will happen, so if I start up there, I have some solution that basically goes down, if I go far enough, and I'm considering the system size L, and L very much bigger than 1, so I will converge to rho plus, no problem. And if I start here, somewhere between these two, then that's in here somewhere, then the derivative is positive, so I will just go up to this constant value of rho. So this looks like a nice solution. Let me call this solution number 1. Similarly for rho minus, well, if I start down here, so below rho minus, then rho dashed is negative. So actually, it can work. So what I've got to do, though, is to start very, very, very close to rho minus. And then I will iterate away eventually. So the solution looks like that. And similarly, if I'm start around here somewhere, then the derivative is positive. So if I started very, very close to rho minus, then I would do that. And again, that would be an okay solution. I think I get a few blank ones. Is it clear what I'm doing? I'm just sketching the possible solutions. And I'm using the fact that it's a long system. So basically, most of the profile will be dominated by these two fixed points. And I just need to check that near the boundaries, everything is okay. Because it's actually, because I still need to determine j, and j will be determined by the boundaries. So remember, I'm here is j is less than a quarter. So this solution 1, what I've got, if I look at this, is that rho plus is the density at this end. So rho plus has got to be equal to rho L. But I know my boundary condition is that rho L equals 1 minus beta. So that's what I need. And then from this condition, where did it go? Rho plus plus rho minus equals 1. I know that rho minus equals beta. But what I need for this to be a good solution, for it to be consistent, first of all, I need rho plus to be the upper fixed point. And the way to ensure that is to have rho plus, it's got to be bigger than a half. Okay, so what I require is rho plus greater than a half. And then actually what that means is 1 minus beta greater than a half. So this implies beta is less than a half. And the other thing I need is that rho 0 rather, is in here. It doesn't work if rho 0 is down there. Then this is not a consistent solution because I'm starting in the wrong place. So I need rho 0 bigger than rho minus. So also I require rho 0 greater than rho minus. So rho 0 is alpha, and it needs to be bigger than rho minus, which is beta. So I need alpha greater than beta. Okay, so that's my conditions. And by the by, J will be given by rho 1 minus rho in the flat part. So that'll just be rho plus 1 minus rho plus, which is just beta 1 minus beta. Okay, so I found, without having to sort of solve explicitly, I found graphically a solution that's consistent for large L, provided these conditions are satisfied. So now let me do the same thing for phase number 2. So for 2, I see that I need to be basically down here. There's a plateau where it's rho minus. So rho minus is equal to rho 0. Okay, and rho 0 by the boundary conditions is alpha. And then, because I know rho minus and plus rho plus is 1, then rho plus is 1 minus alpha. Okay, so far so good. So what I require is, first of all, rho minus must be the lower one. So rho minus must be less than a half. And that tells me that alpha must be less than a half. Also, if I start down here, it's fine. If I start up here, then I have to be sure that rho L is in fact less than rho plus, or else it's not a consistent solution. Otherwise, it would do something else. So rho L has got to be less than rho plus. And rho L is 1 minus beta. So this is 1 minus beta less than, so it's 1 minus beta less than 1 minus alpha. So I end up with beta greater than alpha. So there are my conditions. And you see it's sort of the reverse of this. But, okay, when we sketch it out, you'll see that this leaves still a gap. There's another phase that is not covered by these solutions. So the other possibility, remember this is for J less than a quarter, when we had these 2 fixed points. So alternatively, we can consider J greater than a quarter. Now, in that case, rho dashed is less than 0, because I can just look here, and I see if J is bigger than a quarter, it's all the derivatives are negative. So my profile is going to look something like the following. Okay, so I've drawn it, it's down here, it's sort of nearly flat. And the way I get that, and okay, this is a little bit subtle, so I just tell you what is the self-consistent answer. I need to ensure it's sort of flat enough. In fact, what I need is J equals a quarter plus some constant over L squared, where L is the system size. But just to trust me that that is the result. It's a little bit tricky to show, but that's what comes out. So then, here, you see the derivative is of order 1 over, in the middle somewhere, it's becoming 1 over L squared. So it's a very small derivative, so it's a flat profile. And, okay, so what are the conditions that we need? Well, remember this is rho, and this is from 0 to L. This is x. So we need at 0 that rho 0 is greater than a half, and rho L is less than a half. Sorry, I should have said this density here is, of course, a half, because that's, right. If this curve is down there, that's where the derivative will be. That's where it will be flattest, is at rho equals a half. So rho equals a half should be, yeah, it's there, and this should be around about half of the system. Okay, so this profile works. So the conditions of rho 0 is alpha, so I need alpha bigger than a half. And rho L is 1 minus beta. So if I think about it, it's actually beta needs to be bigger than a half. And then what we find is that those three, that completes the phase diagram. We found all the phases. So we didn't have to solve any equations. We just had to sort of sketch the graph. The other thing to note, one thing I'll comment on here, again, if we work things out, I'm not going to do the details. So if we're, let's say this is x, if we're far away from this boundary, but we're still very much less than the system size, so we don't sort of see the other boundary. So then this is some decay. In fact, the decay is rho equals a half plus, well, it's 1 over 2x. And that's an x bigger than 0, very much less than L. So we're in there somewhere. The decay goes like 1 over x. And the reason I mention that is that, okay, that's something the mean field theory predicts incorrectly. But I'll come back to that. Okay. So now we've got our phase diagram. So just to recap, the phase diagram is basically the limit that L goes to infinity. That's when we get these different solutions emerging. The other thing I forgot to mention, this one here, I've got J equals beta, 1 minus beta. In case 2, J is going to be rho minus 1 minus rho minus, which is alpha, 1 minus alpha. And here, J, in this phase, is going to be a half times a half, because the density, bulk density is a half. So it's a quarter. Well, we know it's a quarter plus A over L squared, which, you know, is going to a quarter as L goes to infinity. Okay, so we can draw our phase diagram. This is alpha, this is beta, and the half is significant. So we have something, it looks a bit like a flag, this sort of thing. And if you can check that down here, if I've got it right, is region 1, corresponding to solution 1. This is region 2, and this is region 3. So the usual names given to these three phases are, well, it's kind of obvious. So the 1 is where we have the upper fixed point, so the higher density one. So this, okay, I won't write out. HD is high density phase. Up here, the fixed point density is less than a half, so it's LD is low density. And here, the density away from the boundaries is a half, and the current is a quarter, and that's actually the maximal current that you get. So here, this is, for the MC, is a maximal current phase. So in the low density phase, we've got, just to summarize, the bulk density is alpha. J is alpha 1 minus alpha. In the high density phase, the bulk density is 1 minus beta. J is beta 1 minus beta. And in the maximal current phase, bulk density is a half, and J is a quarter. And you can check that that is the maximal current. So these are different phases. And remarkably, the phase, this is just, we got this within this crude mean field theory. The phase diagram is correct. There's a few little things the mean field theory gets wrong, which are actually important things, if you're interested. So I'll go through them. I just want to stress that we can genuinely consider these lines as phase transition lines. So the transitions what you'll notice is across the transitions, J is always continuous. So J is the expression for the current. The value of the current is always continuous. And so at the maximal current high density transition, or maximal current low density as well, so that's these two transition lines. Then rho, the derivative of rho is and also the second derivative of rho is discontinuous. So we can think of this as a second order transition. So why do I say second order? Well, to give the game away, it's the derivative of J. That's the one that's discontinuous is the second derivative. And effectively, J plays the role of a free energy. So if you remember your classification of equilibrium phase transitions, or the Landau theory is the derivative of the free energy. The discontinuity, sorry. The derivative of the free energy at which your discontinuity appears is the order of the phase transition. So that's just the language I'm using. So basically, it's a continuous phase transition because rho, the density, is continuous. On the other hand, this line here, which separates the low density and high density phase, then the density itself is discontinuous, which is kind of interesting. And it's the first derivative of rho, of J, that's discontinuous. So we say that this is a first order transition. And on this transition line here, the profile from the mean field theory actually looks like this. So, if you like, you have phase coexistence between a low density phase and the high density phase. So that's like a first order transition, and you have phase coexistence. So just to see that you have this jump in the density, if we're down here, where alpha and beta are low, in the high density phase, the density is 1 minus beta, which is nearly 1. Whereas in the low density phase, which is just across here, the density is alpha, which is near 0. So you get a big jump in just when you go across that line in the density. So it's a discontinuous transition. Okay, so, okay, good. I think that's what I wanted to say. So on that line, okay, this is what we call a domain wall. I leave it as an exercise. So I've solved these equations graphically, but also you can actually find the solution of going back here. Where did it go? This equation. You know, if you like to write down the exact expression, you can. And basically, to give you a hint, the solutions will look something like rho equals a half plus a half, and then I've got some constants here, v tanh dx minus x naught. That's for phases 1 and 2. And rho equals a half minus a half v tan of vx minus x naught applies to phase 3. And you need to fit v and x naught to satisfy the boundary conditions. So you need to show that these satisfy equation 4. And then if you choose v and x naught appropriately, okay, you found the solution. I find that harder than doing it graphically. Doing it graphically, I think, is clearer what's going on. But if you like such things, you can give it a go. Okay, I'll clean the boards, and then we'll move on in the second half. Yeah. Okay, let's just say it is. I'm saying that that's what it comes out of this calculation. Well, that's all I mean. I mean exactly what I said. That the second order transition is the second. J is always continuous, and you can sort of argue that that must be the case. I won't get into it. And then you see J becomes singular at the phase boundary, and you can look at which derivative is discontinuous, and that's what you get. And then I'm saying, oh, there's some analogy. It's very similar to what you see in equilibrium. And in the second half, I will give some justification for that. Okay, yes. 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 But that's because you know the exact solution. This is the mean that, okay. Yeah, sorry. I'll come to that. So there's certain things the mean field theory gets wrong. And you've pointed out one of them. So I don't want to confuse people. What I've written is correct for the mean field theory. It's actually wrong. In the exact solution, we get a different form for, where was it? This decay here. And there's other things that are wrong as well. So another thing that's wrong is, I told you that to make this work, I had to take j a quarter plus 1 over L squared. It turns out in the exact solution that's wrong. It's actually, the correction is 1 over L. So you might think these are minor little things, but actually they're very significant, and I'll try and explain why. And there's a few other things it also gets wrong. The phase diagram is actually a little bit more, it's correct in total, but there's a few details that are a little bit different, and I will describe them in the second half. So let me clean the boards now, and we'll get on to that. Okay, so in the first half, we did the open boundary exclusion process, and we did the mean field theory, and we saw it's got a very interesting phase diagram with different phases and different kinds of phase transitions. Let's go back now and ask whether we can solve exactly. So I told you in the first lecture, it's often very difficult to compute non-equilibrium stationary states. Generally, it's a very difficult problem. Turns out in this case, you can find the solution, and it has quite an interesting structure. So what I'm going to do is just to present the structure to you, and then we'll sort of do a sketch proof to convince you that it works. And so this solution is known for reasons which will become apparent as matrix product solution. And it gives the exact stationary state for open boundary TASEP. So, okay, so yeah, so now this is section 4. Section 4 will be a little bit short, and hopefully I'll finish it today. Okay, so let's make the matrix product. Okay, the A stands for ansatz. Sometimes it's known as matrix product ansatz. So let's guess that, okay, we construct our stationary state probabilities as follows. So if I have, I'm going to have some configuration, which is, I don't know, a string of 1, 0, whatever. String of zeros and ones. So everywhere that, and remember tor I, my indicator is 1 or 0. So wherever tor I is 1, I write a matrix. Okay, I don't know their matrix. Yeah, it turns out they will be. D. That's just the conventional notation. And if tor I equals 0, I write a matrix E. Okay, so all I'm saying is that, e.g., if I have some configuration like 0, 1, 0, 1, then I write E, D, E, D. Okay, but that's just a product of matrices. What I want is a probability. So to get a probability out of, or get a number out of a matrix, I kind of want to sandwich the matrix between a row and a column vector, right? Then I get a number. So let me do that. So I let, and again, I'll use bracket notation. Don't get worried by it. Oh, it's just a lazy notation for row vector, column vector. So let me call W and V. So W is a row and vector, and V is a column vector. So then finally, okay, if I sandwich this between the row and the column vector, I get a number. Only thing is, probabilities need to be normalized to add up to 1. So let me, just in case I haven't normalized things, let me put in a normalization. Okay, and I'll dare to use the symbol Z. Okay, this force I took with Z4. So if you think about it, remember, in equilibrium system mechanics, Z, the partition function, it came in the same way, just as a normalization. But actually, it turned out to be significant. It's the same story here. I'm sort of sneaking in a Z, and this will turn out to be the crucial thing. Okay, so that's it. And I'm saying, but at this stage, it's just an ansatz. So it's a way I can write all the probabilities in this way, and okay, I can do that if I like. There's no guarantee that will work. So just to be more general, I can use some notation. For a general configuration with tors, and I'm on a system of size L, normalization will be ZL, I'll have a W in a product of I equals 1 to L, and I can write the matrices as X of 4I. And so X1 is my matrix D, and X0 is my matrix E. Okay, so far, so good. So, has everyone got that? It's just quite easy. It's quite simple. Just I write a product of matrices. So then let's just, first of all, dispose of Z. So my partition function, or sorry, I'm starting to go to partition function. Let's stick with normalization Z. So ZL will be, okay, it's the sum. If I think of this as a weight, it's the sum of all possible weights. So the sum will be over all possible strings of zeros, ones. So basically, it's the sum over each tor I equals 0 or 1 of this W, and then product over I xi of tor I. So if I just do that, then I just get a D plus E for each site. And this will be W D plus E to the L B. And I'll call, for convenience, D plus C equals C. So that's the normalization dealt with. But first of all, I have to go back and think about the D's and the E's. Okay, a few more things. So if you're happy with this, then I can actually write down correlation functions and densities quite easily within this matrix formulation. So in the steady state, if I want the density, well, the density, remember, is an average over this indicator variable, so I want there to be a particle at site I, and I want to sum over the probabilities of all configurations with the particle at site I. So when I write the configurations as the matrix product, it's all matrix products with a D at site I, because this tor becomes a D. And if I think about that, it actually will be, okay, I'm going to have a D at site I, and when I sum over what happens at all the other sites, I just get C's. That will generate all the possible configurations with a D at site I. So I'll have a C to the I minus 1, C, the whole thing is length L, so L minus I. And then over my normalization ZL. Okay, maybe I went a little bit quickly there. It's actually quite simple. Yeah. So all that's happening is that tor I means that I want to average over all the configurations with a particle at site I, and so that becomes a D, because I'm writing a D whenever there's a particle. And then I can sum over everything else for the rest, and that gives me C's everywhere else. Okay, it's clear once you got that. Once you see it, it's easy. And similarly, my J, which is tor I 1 minus tor, I plus 1. Okay, here I'm averaging over configurations with particle at site I, whole at site I plus 1. So I need a D at I and an E at I plus 1, and then the rest is whatever. So I just put C's everywhere else. So it will be a D, E, C to the I minus 1, C to the L minus I minus 1 if I counted correctly. So you see all these correlation functions I can write down. Once I've got the hang of it, I can write down easily. But still, I need to go back and prove that this way of writing probabilities works. There's no reason a priori for it to work. What I'm going to tell you is that it works when you have relations. So that was for A. That have been, okay, are usually referred to as informally as the quadratic algebra. So actually, these are sufficient conditions for the matrix product to work. for this case. And it's the following relations. So D times E equals D plus E. D acting on the column vector V is 1 over beta times V. And E acting on the row vector is 1 over alpha times W. So what's that saying? Well, it's just saying that these vectors V and W, these are eigenvectors. Well, V is an eigenvector of D, and E is an eigenvector of W. So that's fine. We like eigenvectors in physics. This one is, it seems very simple, this relation, D equals D plus E, but it's significant because it tells you that if I have a product of two of these things, so this might occur in a 2-point correlation function or something, for example, it actually reduces. And this is the key thing that makes it solvable. But I still haven't written down these conditions and said this is what works. I haven't shown you why. So I'm going to give you a sketch proof. Okay, I've got enough time, I think. Actually, so first of all, let's also see some more utility of this. So you can see that let's see how using these, we see that the constant current is generated. So as a check that these make sense, remember our current in the stationary state, we need to have a current. That's constant. Remember the current in is alpha 1 minus tau 1. And so in the matrix product, this becomes alpha. And then having a 0 at site 1, I write an E, and then it will C's everywhere else. And then in the bulk, I've seen here that the current can be written C I minus 1 D E C L minus I minus 1. And finally, at the right-hand side, the current is beta times the density at site L. So it becomes beta W C to the L minus 1 D. Because the D here means that we have a particle at site L over ZL. And then you see straight away that these equations ensure a constant current. So I see using, so if I call this the quadratic algebra, so using the quadratic algebra, this actually becomes all of these. So E times alpha on W just becomes W. So I get W C to the L minus 1 over V over ZL. Similarly here, DE is D plus E. And remember, D plus E is equal to, by definition, it's C. So this DE equals C, and you see I get C to the L again. And finally here, D acting on V gives me 1 over beta V, and again I get C to the L. So all these expressions are the same when these conditions hold. But that still doesn't prove it's right. It's sort of encouraging. So from that we actually get, someone asked a question earlier, and I said that the current plays the role of a free energy. So this is now suggestive, because what I've shown here is that J I can write, so remember, this thing is actually ZL minus 1. So really it's J in system size L. And that starts to look a bit like some kind of free energy. Okay, let me not get into details, but it's getting towards the form of a mathematical form of a free energy. Okay, so the big job that we have left is to convince you that this actually works. So I'm going to make a okay. So I want to give you an idea of why this form for the matrix product, when we have these conditions here, why that satisfies the master equation. And what I'm going to do, I'm not going to do the general proof because the notation gets a little bit heavy. I just want to give you an idea for certain types of configurations. And then once you see the pattern, then you can easily construct that it's going to work for all the configurations. So I'm going to take a particular configuration, and let me write it as it's got zeros, let's say m zeros, n ones. So hopefully this, what I'm writing, okay, it's an slight abuse of notation, but it should be self-evident what I mean. So there's m zeros, n ones, and let me say r zeros and s ones. That's I want to look at this type of configurations where it's two clusters of ones. Okay, so then the weight, so the matrix product, again, I'm going to use a slight shorthand notation. Instead of writing out the Bra and Ket vectors, I just write a bracket like this and like that. So this will become this is meant to be shorthand for the vector W. Then I'm going to have e to the m, d to the n, e to the r, d to the s, and then that's a shorthand for the vector v, just to save me having to write everything out loads of times. Okay, so the master equation for this kind of configuration becomes the probability of this 0 to the m, 1 to the n, 0 to the r, 1 to the s. Okay, I'm going to have a number of terms here. Okay, so particle can enter with rate alpha, so that I leave that configuration with minus alpha p 0 m 1 n 0 r 1 s. I can get there from this, the first of these ones coming from there. So then I have 0 m minus 1, 1 n, 0 m, yeah, no. 0 to the power m minus 1, 1, 0, 1 to the power n minus 1, 0 to the r, 1 to the s. Then, okay, I can leave from this one hopping forward. So I get a minus probability 0 m 1 n 0 r 1 s. I can get into this configuration from this one having come from there. So I get plus p 0 m 1 n 0 r minus 1 1 0 1 s minus 1. And finally, I can leave from this one leaving, which it does with rate beta. So I get minus beta p 0 m 1 n 0 r 1 s. Okay, this is not very good board management. So I now want to look at the stationary state. So when this is equal to 0, and then I'm going to replace these, okay, I'm going to write these in their matrix product forms. The stationary state becomes 0. So here I'm going to have minus alpha e to the m, d to the n. And what I'm going to do, I'm going to make a note of where the transition was. Okay, we'll see why in a moment. So here is from this particle coming in. We lose probability, so let's just make a little note there. Okay, so d, n, e, r, d, s. Then I've got plus e, m minus 1, d, e, e, n minus 1, no, d, n minus 1, e, r, d, s, minus e, m, d, n, e, r, d, s, and that's from this guy hopping forward. And plus e, m, d, n, e, r minus 1, d, e, d, s minus 1. And that's from this one going forward. Okay, hard work will be over soon. And minus beta e, m, d, n, e, r minus 1, d, s. Okay, so that's what I need to be satisfied for this class of configurations. And what we can see now is just by take this right-hand side and use these rules here precisely where I've done the underlining. So that's where the action is. So let me take the right-hand side. Last time. Oh, yeah, you're right. Yeah. Thank you. Okay, everything else right? So that's, there was where the action is. So the first term, I lose, remember, E, so this is W. It's an eigenvector of E, and I cancel the alpha. So I have minus E, m minus 1, d, n, e, r, d, s. We're going to run out of board soon. So dE equals d plus e. So I have E, m minus 1, d plus e, d, n minus 1, e to the r, d to the s. Here, minus e, m, d, n minus 1, d plus e, e, r minus 1, d, s. This one here, plus e, m, d, n, e, r minus 1, d plus e, d, s minus 1. And then finally, this one here, I get rid of one of the d's and I cancel the beta. So minus e, m, d, n, e to the r, d to the s minus 1. Okay, so that's the hard work and the hard writing over. Sorry if it takes a little while to write out. And now now the magic happens. That I've got this bunch of terms, and I can see m minus 1 n rs with a minus. This one will be m minus 1 n rs, so it cancels with that one. This one, I've got m n minus 1 rs. That's going to cancel with that, which will be m n minus 1. Yeah, with the e rs. This one, I've got m n. No, what did I say there? Did I get that? No, that's right. Okay, then this one is m, the d here, so n, r minus 1s. And that's m, n, r minus 1, and then this term will give me s. And finally, This one is MNR S minus 1. It cancels with this one, MNR S minus 1. So you see there's a pairwise cancellation. So you can formalize that, and if you use a heavier notation, you can show that this pairwise cancellation occurs for any configuration, not just the ones of the type I found. Right? So basically, we're assuming this cancellation mechanism, and the way to do that is with that quadratic algebra. Okay, so this is a very nice thing because it gives you an exact solution valid for any system size. There is one final little thing to check. So far, we've assumed that these things exist, right? That we can find D's and E's, et cetera. I mean, there's one little thing that could go wrong. We could possibly find some nice relations, but actually those relations were somehow inconsistent. That they simply weren't consistent with each other, and then the whole thing would break down. So we need to be sure that these are consistent, and the surefire way of doing that is to actually write down the representation. Then you know it's okay. So let's do so. Oh, it's over there. Okay. Okay, so let me call this 4D, representations. So there's one special case, as it turns out, and I'll just quote this to you. So in the case alpha plus beta equals 1, then we can actually just use numbers or scalars for D and E. If we want to use a scalar, then clearly D must be 1 over beta and E must be 1 over alpha, if these things are just numbers. So if alpha plus beta equals 1, we can take D equals 1 over beta and E equals 1 over alpha. Then DE will be 1 over alpha beta. And because alpha plus beta equals 1, this equals 1 over alpha plus 1 over beta equals D plus E. But that's a very special case. So that only works. Remember, this is a line on one line in the phase diagram. So that's a special line where things simplify. And more generally, that's not going to work, so we need matrices. Okay, it's not difficult to show that your matrices are, okay, the D's and E's don't commute. And you can also prove that they can't be finite dimension. If you want to use them for any system size L, then in fact they must be infinite matrices, which sounds a bit scary, but when you write them out, they're not. So, okay, let me just give the game away, and a simple, for the general case, we can always use the following representation. Hopefully you can read this. So I can take D, and I'm going to write it as it's a semi-infinite matrix. So I'm going to start here. So if you like, I can start with my row number 1 or 0 if I want to start at 0, and then it goes to infinity that way, and also that way. So I'm going to put a 1 here, and a 1 there. And similarly, it's 1 along the diagonal, and 1 on the superdiagonal. Okay? So just 1, 1, 1. And then zeros everywhere else, and so on. And E, similarly, I put a 1 down the diagonal and 1 on the subdiagonal. Okay, so I've got 1, 1, 1s and 1s, and so on. And then zeros everywhere else. And then I see, let's just do the multiplication. I don't know if you can, well, do it here. DE, okay, I'm going to have row into column, so 2, 1, 0, and so on. The second row is 0, 1, 1. So I get 1, 2, 1, 0. And so on. And you see that this is equal to D plus E. And finally, my vectors, the column vector V, I can write as 1 B, B squared, and so on, where B is 1 minus beta over beta. So you can check that D acting on this, the first element will be 1 plus B, and 1 plus B is 1 over beta, which is what I want for eigenvalue 1 over beta. Second element will be B plus B, so it's B times 1 plus beta, sorry, B times 1 plus B, which is B times 1 over beta. So it works, it's an eigenvector. And similarly, W is 1A, A squared, etc., where A equals 1 minus alpha over alpha. Okay, so these matrices work, and so this matrix product works. Okay, let me continue. So I want to give a flavor of how you go about calculating with the matrix product. So remember, one thing I highlighted to you is that the current is a ratio of partition functions. And remember, the current determines the phase diagram. So a good thing to do, well, sorry, I'm already calling a partition function. It started off as a normalization. Essentially, it plays the role of the partition function. So I want to calculate this thing, Z. So let's spend a few minutes trying to do that. So that was representations. So let's write. Okay, so the first approach is what I would call this the brute force approach. I just calculate for L equals, well, let's make it easy. I start with L equals 0. And then L equals 1, and so on. And then I see the pattern. I guess the answer, and then I can prove the answer by whatever means I choose, usually by induction. So let me just show you what happens. So first of all, I want ZL. If L equals 0, right, there's no site. So let me say for L equals 0, Z is just this L. Z0 is just this scalar product. And let me assume that I can take that to be 1. So with a few caveats, I can do that more or less without loss of generality. Okay, so then if L equals 1, I have WD plus E. Remember, L equals 1 is one site, so I have just, remember, Z L is C to the L, and C is D plus E. Well, I've rubbed off the quadratic algebra. That wasn't very smart. So, let let me just remind you up here that D E equals D plus E equals C, D V equals 1 over beta V, and W E equals 1 over alpha W. Yeah, I should be writing in yellow, right? Okay, so for L equals 1 over D plus E, so this is in fact D acting on V is 1 over beta, and E acting on W is 1 over alpha. So it's 1 over beta plus 1 over alpha. And that's with assuming WV is 1, which I can do without loss of generality. Then where it gets more difficult is L equals 2. So then I've got D plus E squared. And when I get D plus E squared, I multiply it out. I'm going to get D squared plus E squared plus ED. Then I've got DE. And let me reduce that to D plus E. Then you'll notice that each of these terms, again, I can use the eigenvalue conditions. Right? They've all got, basically, they've all got D's on the right and E's on the left. So this becomes 1 over beta squared plus 1 over alpha squared, this, plus 1 over alpha beta. Then these two, I'm going to get 1 over beta plus 1 over alpha. So you see what's happening. Each C to the N, I can write in a way that I've got D's, a sum of terms with D's to the right and E's to the left. And then once I've got that, I can just turn them into alphas and betas. And if I keep doing that, then I get the general formula which is as follows. Okay, the details for this lecture isn't too important. I'm not going to take it much further. But the important thing is that you can get a relatively simple closed expression. So what we end up with is a sum. So P here is just an index. So P equals 1 to L. And then there's a combinatorial factor. So it's 2L minus P minus 1 factorial. L factorial. L minus 1 minus P factorial. And then 1 over alpha to the P plus 1 minus 1 over beta to the P plus 1. Sorry, that's a little bit cramped. So you see it's a relatively simple expression. Now, okay, I've got 5 minutes left. The way I did it there, if you noticed, I simply used the algebraic rules. And I deduced this. Now, it depends if you like that. That's an appealing approach for some. The other way to go is to use the representation. So an alternative way is to note using the representation so I can write WC to the LB. It's going to be 1A squared, so on. Then this big matrix 2, 1, 1, 2, 1, 1, 2, 1 with zeros here. And then 1B, B squared, etc. And this is to the power L. So usually, what's the easiest way to compute matrix elements of powers of matrices? Sorry? Yeah, okay, good, you got it. Yeah, so the natural thing is your physicist is diagonalize. we like to diagonalize matrices. And that's another way to go. You can diagonalize this matrix, and you'll find that there's a spectrum, and you can then, you end up using Chebyshev polynomials if you like that route, and you'll get to the same answer eventually. And there's various different routes. There's other ones that, okay, I don't want to spend too much time. You can also use generating function techniques, if you like, sort of that kind of thing. And that's actually the fastest way to get to the answer, is with generating functions. And I don't want to do that. It's a little bit tricky. I can explain it to you, so people are interested, but it's a little bit sort of tricksy. So let's leave that. But in any case, you get to some exact expression. And then, if you want to take the calculation further, we want the, as I said, for J, we want the ratio of partition functions for large L. So then the game becomes, you want to evaluate the asymptotics of this expression. Again, there's ways of doing that. I won't go into it. But what I want to say is, so what do we learn from all this? So the result from the exact solution. So firstly, the phase diagram that we derived with the mean field theory in the first half of the lecture, so to call that the mean field phase diagram, is in fact correct. Okay, up to a few embellishments. So what I mean is that flag shape is the correct phase diagram. But there's some important little differences with mean field theory. So I want to note these, and these might seem insignificant, but actually they're pretty significant. So in the max current phase, in fact, we can compute J, the current in a large system size L, and it's a quarter of 1 plus 3 over 2L, and so on. So first of all, this is different, the 1 over L, that's different. And also the coefficient 3 over 2 turns out to be significant as well. This exact value 3 over 2 is important. And it's characteristic of this kind of system. So this is an important result, even though it might seem a little bit insignificant. Also, again, in the max current phase, the density, when we're far away from one boundary, we're moving away from one boundary, but we're far away from the other end. Somebody pointed out that the mean field diagram gave the wrong result. So the right result is, in fact, that the density, okay, nearly there. It decays, okay, there's a coefficient here, which again is significant, the exact value of this coefficient. And in fact, this is J. I think I used X in the first half. So it's the distance from the boundary. This is when J is very much bigger than 1, but very much less than L. It goes as J, the square root of J. So it's a slower decay than the mean field theory. We can also calculate correlation functions. So remember, the mean field theory essentially ignored correlation. And what one can show the correlation functions, if I take something like tau I, tau j, minus, so this is called the connected correlation function. So if there were no correlations, this would be 0. And in fact, from the exact solution, this is of order 1 over L when I and J are of order L. So if we're in the bulk, far away from the boundaries, the correlations are of order 1 over L. Okay, let me just finish. There's more little things I could say, but time's up, so let me finish there. So any questions on TASEP phase diagram? Yes, okay, sorry, of course. This is a function of I minus j, but I'm saying that the scaling is of order 1 over L. So yeah, this depends on, yeah, it's a function of I minus j in there.